All right. Hello. Let's see, is my mic working all right? Can everybody hear me all okay? I guess the mic is more for the stream's benefit. But yes, I'm Kate Compton. I'm here from the Expressive Intelligence Studio at UC Santa Cruz in sunny Central California. And yeah, I was going to give a talk today, and I wanted to give a talk on something that was really practical. And so this is some stuff that I've used to create what has turned out to be like one of people's favorite of my creations. This is a procedural flower generator, and then you can pick on the flower that you like, let's say this one, and it makes more of those. And so you can procedurally iterate on this flower, and it makes people happy. And that's one of my favorite things about procedural content generation is that you feel this surprise and like wonder that people can like click a button and something magical happens. So I thought I'd give you a very practical presentation today on why that was made in approximately 4 hours for class I was teaching, and why this procedural generation came together really fast, ended up being very useful for me, and how you too can make stuff that goes together really fast and has wonderful affordances. So this talk is called Let It Grow. You can sing the song in your head. Practical procedural generation from the ground up. A lot of PROCJAM talks, I watched some of the ones from last year, have these big, wonderful ideas of what it means to generate things, what sorts of wonderful things we can generate, like what sorts of big, beautiful worlds that we can build. But often they don't have sort of very practical, like you're a first-year student in CS and you just kind of want to build something, like how do I even get started? Practical advice. And so that's what this talk is about, and also about how to make flowers. A little bit about me. I'm Kate Compton, like I said. I worked on Spore. I worked on SimCity. I'm famous for making the planet, well, famous, quote unquote, for making the planets on Spore. These are my babies. I'm Galaxy Kate at all the things. And if you want to play with the flower thing, it's in with my secret app stash at this very secret address here. So a lot of times when we design a game for PCG, we design it from the outside in. We have some sort of super awesome game idea. So this is my game called Super PCG World. It's going to be amazing. It's got some cool content needs, like it needs some terrain, and it needs some dungeons, and some cool creatures, and maybe some rad music. And then once you've got all these content needs, you're like, OK, well, now what am I going to actually make those with? How do I make all these things that I just said I was going to make? And this seems totally logical, because everybody wants to start with a big, cool game idea. And especially if you're in AAA, you actually may be legally required to start with a big game idea. Like, we have the James Bond license, so we want to make a game for 8 to 12-year-old girls, and it's going to have microtransactions. Please produce this game. But especially for game jams and for student projects and for indies, we have the option to not do this. Because what happens when you do this, and this is what I've seen on Spore and SimCity and a large number of other projects, is that your data structures start fighting back against your content needs. Like, I can't actually figure out a good data structure to make that particular kind of content. There's constraints or weird stuff going on. And then even if you get cool content, it starts fighting back against your awesome game idea. We saw this a lot on Spore. This was like the entire process of making Spore was Will Wright had presented this amazing, cool Super PCG World game idea. And as we started making the content, actually the content ended up generating pretty well. But by the time we had started making the content to get to this beautiful game idea, it didn't work out. There was this sort of like, wouldn't it be great if the players could create anything? We're like, yeah, we got that. And what if it meant, like, what if all their choices mattered? And it's like, that actually is a fundamental contradiction, and we couldn't solve that. Though we tried. We really tried. Sudan SimCity as well, where some of the transit generation or like the traffic simulation ends up fighting back against the, like, I'm an all-powerful mayor feeling. And people did not like that at all. I would like to propose that, especially for the stuff we're doing this week, there is another way. Just let it grow. So this is treating PCG as the seed from which surprising things grow, not necessarily the thing that you wanted, but being flexible for that. So this is game design from the inside to the out. So we're going to start with data structures. And from our data structures, we're going to see what kinds of cool content and interaction can grow from there. From the cool content we get, we can then come up with an awesome game idea built around that. This works much better from doing a lot of indie stuff. This pattern has worked so much better for me than it ever did in AAA, the outside in. So data structures. I'm not sure how many people here are game students? A couple of game students. Indies. How many of you would consider yourselves like novice programmers? A couple of novice programmers, cool. And raise your hands on the stream if you're a novice programmer. Wow, great. So data structures, kind of why am I talking about data structures at all when I could be talking about cool content? Well, data structures are these things that are like numbers, strings, arrays, graphs, not like visualization graphs, but like connectivity graphs. They're how we represent the world so that the computer can understand it. So this is how we're feeding information for the computer to understand. But in PCG, they're also something kind of different. They're a way of storing information that can be used to regenerate content. So you can almost think of them as like a seed. They're a seed that has the DNA from which you're going to grow this amazing tree. And depending on how we change that DNA or how we store that tree, or how we store the tree's DNA, we could probably grow very different kinds of trees. You know, you're gonna need different storage for a tree than you will need for like a jet engine. So the talk today is going to be showing you this big, like it'll be this giant tour of PCG, many ways to interact and generate things, lots of the things at the bottom, genetic algorithms, human guided evolution. Like this is all in the next 15 minutes, but just through the lens of one single data structure. This is our hero for today. It's the array of floats. This is our hero. It is one of the simplest data structures. It's really easy to program. It's easy to understand. It's just an array of numbers. We're not talking about like connectivity graphs where you have to like figure out like tree traversal algorithms. It's just like, here's some numbers. You can do different things to the numbers. And there's clear affordances. Like, what can we actually do to a set of numbers? Like, we can change the numbers a little bit. We can add things to the numbers. We can make an array that's kind of like that. We can clone that array and like change it a little bit. So yeah, on the generation side, you can generate lots of things from an array of numbers, and I'll show you some of these. But like, you know, geometry, texture, movement, behavior. You can also interact with this array of numbers in a lot of different ways. You know, maybe you have a slider. So if anybody's seen like the giant wall of sliders that you have in a lot of creativity tools, you know, that's one way to interact with these. Or data streams, gestures, simulation, evolution. This is kind of a roadmap for where we're going in the next few slides. And you can also use this to make new gameplay. So as far as generation, there's things like generating geometry, generating the 3D mesh, generating textures, generating movements and behavior, or movements, and then generating behavior. This is a little dance simulator that I made. That's actually, this is the DNA of the dances that are going on right there. So those are made from an array of floats. Some of these are made from things slightly more complicated than an array of floats, but like you can do all this stuff with just an array of floats, or with any complicated data structure as well. But today we're keeping it small. Interaction. This is an app that, OK, you can sort, no, it clipped off the top. Oh, yeah, there we go. So this is an app that I made where you make a procedural snowflake, and you can slide the sliders to change the trajectory of the particles that are generating the snowflake, and that allows you to, like, the inputs here is an array of the inputs here is an array of floats that change the trajectory of these particles, and so by changing the floats, I change the shape that's getting made on the snowflake. This is another one. This is a sort of gestural interface of a pennant maker that I made that's generating 3D printable geometry. And you can just kind of squiggle, and then it's going to extrude stuff along there. This is a sort of Beard of Rainbows complementary Doge mirror thing that I made. I don't really know where it's going, but it was a lot of fun. And it's taking as input, so there's a library in JavaScript that will track your face really well. I'm forgetting the name of it, but ask me later. But that changes the sort of facial position into a string of floats, which are updating every moment. And then you can use that to do really cool procedural generation. So a little bit about generation. So a lot of this is super elementary for those who are like just getting started, but it's actually useful for me to, like, as a 10-year practitioner of PCG, to clarify what I'm actually doing here. So imagine we have this function called generate flowers, and it takes an array of floats. And it can generate a bunch of different flowers. So we have some sort of possibility space of what it can generate. This is what it actually looks like, which is fairly hairy code. But you know, the most important thing is that we have this little module that can take an array of floats and make a flower. And once we have that, we can do some cool stuff. So imagine we can generate a flower. We can generate a flower from a slightly different, or from a very different array of floats, or from a very different array of floats. And that gives us a whole space of flowers. And that's pretty cool. And actually, a lot of PCG systems stop there. Like, once you've got a generator that can generate lots of cool stuff, like victory, you've won. Declare yourself, done. But we can keep going. And let's keep going. So if you feed it similar arrays of floats, or somewhat similar arrays of floats, you should get something that looks kind of related. And so this is feeding those through my flower generator. And you can see we've got a bunch of flowers that all look kind of alike, but all different. They're of the same family. And this is made possible with a continuous possibility space. This means that your flower generation function, if you feed it similar arrays, it will produce similar content. And what similar means can be kind of up to you. And a lot of the things I'm going to show today kind of require this continuous content, or this continuous space. So again, if you're just starting off, things that work well for this are sign functions and noise functions and most algebraic kind of functions. Things that usually don't are like if statements, like switching. Like there's not much, or like an integer stuff. So there's not much continuity between like 3 arms and 2 arms. There's not like 2.675 arms. That's harder to draw. And if you have like a switch statement that's like, if greater than 0.5, draw a mountain. If less than 0.5, draw a river. That's very discontinuous. You can't always avoid it, but a lot of these techniques will work much better with the top ones. So yeah, back to our flower example. Let's imagine now we have an array of floats, and we change it a little. Or we have an array of floats, we generate the flower, we draw it on screen, we change it a little, generate the flower, draw it on screen. We do this a bunch of times. What is this going to look like? What is going to happen here? It's going to be animation. So now we have animation, procedural animation. And this looks like this. Oh. So you can see I'm actually, so this is my flower generator, and each flower is, basically each time I'm picking a flower and I'm iterating slightly on it. So you can see it's, like these flowers are drawn from scratch each time. This is destroying the world and rebuilding it anew with PCG, but because I'm feeding it slightly different values each time, animation. You can even just slide one value back and forth. So this is sliding, I think, position and color back and forth, and that gives me this cool 3D animation of a flower as well. I do a lot of stuff with flowers. Flowers is great for lazy people who want to make pretty things. Nobody knows what a proper flower should look like. They just know that it's like there's some radial symmetry and colors going on. And as long as you can do radial symmetry and some colors going on, it's like snowflakes. That's another like easy peasy one. But then you can also use, so like flowers are super easy, but you can also use it for procedural animation. So here's some animated hands, and this is like an array of floats that are determining like the curl of the fingers, and I just like waggle those with a noise function. Noise functions are great for moving your array of floats around. Here's another one that's doing face generation, and this is just like sliding the array of floats around for like eyelid lift, or actually lower eyelid lift, and then it's doing blink off the top eyelid. I'll show some more of that later. You can use it for level generation. I keep forgetting that I actually had music on a lot of these. Yeah, this is a wave generator that I'm using as a level for for a little like Tiny Wings style sailing game that I made. But like this game wouldn't be much of anything if it weren't for those waves. And so once you have something being generated, you can then use it in a whole bunch of different ways. All right, so that's generating stuff. We've now generated a bunch of stuff. Now how do we actually interact with it? And again, a lot of generators never get to this interactive stage. A lot of them, like, you generate the content, and then maybe the user is playing a game, and sometimes that content gets used, but they're never playing with the procedural generation. So this is how to play with procedural generation. So imagine we have our array of floats, and we've made 3 clones of it and tweaked them all slightly. What can we do with this now? Well, if each one of those is being used to make a flower, and I can look at this and think of which flower that I like, and maybe I like the second to last one there. I say, OK, as the user, I don't see the array of floats, but I can see the flower. I pick that flower. The computer says, aha, I know what DNA was used to make that. I know what seed went into that flower. So now I can make seeds of that seed. And so it makes seeds of that seed. So it will take this array of floats, make some clones of it, mix some flowers, and then you can pick again and again and again. You can imagine this is like if there's an n-dimensional possibility space here. If this is an array of floats that are 0 to 1, we have an n-dimensional cube of side 1. That each array of floats is a point in that space. And what I'm doing here is doing like a little walk through that space. I'm showing the user 8 places that they could go and letting them pick where they're going next. So pick where they're going next, pick where they're going next, pick where they're going next. And this allows them to like wander through a possibility space. You can do this either human-guided. So that, I forgot to put the like punchline slide here. This is procedural genetic algorithms. So now you have a genetic algorithm. Never let people tell you that you can't do genetic algorithms. They look super scary. But all you really need for a genetic algorithm is something that you can change, which is our array of floats, something that you can test, which is looking at a flower and seeing if it's pretty, right? And then a way to change the thing that you can the thing that you can modify into the thing that you can judge. So that's our little flower generator. And then you have genetic algorithms, like I just showed you. Like pick the one that wins, make babies. Pick the one that wins, make babies. You could also do this from the automated metric. These are ones that are like deep physics. Oh, I guess I only put the one thing in the slide there. These are like seriously sophisticated physics simulations of generated walk cycles and how well they are able to move this like little bipedal creature. You can do that. That takes a lot of time and a lot of like physics and whatnot if you're into that sort of thing. Often I'll just do sort of random automatic genetic algorithms. So this is one that it could be either human guided or automatically guided. So this is an alien face generator that, like the flowers that I showed you, it's going to pick one and then breed it. So this is procedurally evolving alien faces. So each time it's going to just kind of move randomly through the space. I could have some sort of metric that I gave it. It was like, pick the most red one. But at this point, I just kind of want to make something that looks cool. So it's just making a random choice each time. You can also make stuff that behaves differently, that interacts with you differently. So does anybody recognize what's on the screen right now? Boids. So this is Craig Reynolds' Boids. It's a flocking simulation. You have this flock of boids, and each of them is like monitoring these 3 forces according to, or like being given these 3 forces based on what's nearby it. So like separation, alignment, and cohesion. But when you actually program this in, you realize that this is like very underspecified because it doesn't tell you how strong each of these should be. Like, how far away should I like keep my flock? Or like, you know, how far away can I be before I start panicking as like a little Boyd sheep that I like need to start getting pulled forward? And you can model that as an array of floats. So now that you have your array of floats, you can generate procedural flocking behavior. Remember that this is the lingua franca here. So anything that happens with this array of floats, you can use all the other stuff with. So I gave my students as an assignment programming these Boids and then using that in the like select and check genetic algorithm I showed you earlier. So you could have a flock of Boids, like a whole bunch of different little flocks, and you picked out which one's behavior you liked best. So you can like do human-guided evolution for flocks. Behavior and force, let me check the time. Yeah, I'm doing all right. Yeah, so these are some stretchy little ragdolls that I made. And these are using array of floats to control the body dimensions. So this is using some sort of straightforward procedural generation, which is like make different shaped bodies. But it's also controlling how strong all of the connections between the bodies are. So these are basically bags of springs. And so some of the springs are stiffer, some of them are looser, some of them are stretchier, some of them are bouncier. And then a third array of floats is controlling when these different forces get applied. And so that gives you an array of floats that controls body shape, an array of floats that controls body sort of flexibility. You know, everything from like, you know, really loose dancer to like really stiff dancer. Oops, sorry. And then one that controls the actual choreography. So you can evolve all those separately, which is the goal of this project eventually. Input streams. Again, this is just one way that you can control an array of floats. So here is a music visualizer, which is giving me, helpfully enough, an array of floats. Here are a very simplified version of the dancers from the previous ones. And each of them has a little dance responder that you can think of as kind of a sentient tribble that is like parasitically attached to some node. And it's listening for a specific frequency. And when it hears that frequency, it is going to yank in a particular direction. So that's the DNA of the dance is like an array of floats controlling which limb, let's see, which limb, which frequency, and which direction all these are going to. So these are each different like little specimens of dance. Motion-controlled interaction, because I promised I was going to get to this as well. So a lot of stuff has been done with Kinect and leap motion. Is anybody doing the leap motion jam? Just me then. Hey. Hey, leap motion. Let me win. So like a lot of these motion control things give you back these sort of like hand positions. And sometimes they do more advanced mathematics like to be helpful to you, but they also give you back these arrays of floats, which are all the positions of either the hands or the body. Mostly what people do with this device is take this huge fat pipeline of data, like this giant matrix of floats that's getting passed to you 60 times a second, or like 20 times a second, and compress it down to like a Boolean value every 5 seconds. Did you do the pose? Did you do the pose? Did you do the pose? And so it's like losing all this wonderful data. But we know what to do with an array of floats. Especially an array of floats that's going to be changing over time. We can use that to animate stuff. And I will show you that in a sec. Here's one that I did. This is not doing anything particularly interesting at the moment. I'll show you that later. This is using the array of floats to do like 3D painting. But this is one that I like much better. This is the Treachery of Solitude by Chris Milk. This is not turning it into a button. This is taking like the position of your hands, and I guess you can't really see it on this GIF, but as you spread your fingers, it's extending a feather from each finger, like along the direction of that finger. So it's able to like take this constantly changing array of floats and turn it into a constantly changing animation. And people get this immediately. Like you would think that it would take time. If you told somebody that they were going to be interacting with something with like a pipeline of 20 floats like 60 times a second, they'd be like, I can't even think that fast. But as soon as you have them waggle their fingers, they're like, oh yeah, no, I can totally predict what's going to happen like when I waggle my pinky. There's great videos of children using this, and they pick it up like instantly. And this is fun just because, oh, I don't have, never mind. Forget that slide. Well, no, because this is a 3D space, you can do all sorts of really interesting stuff making sense of that space. A lot of times what we get in PCG is this kind of endless feed of content, and showing your user where they are in this content or which part of the content makes sense. You can give them landmarks, so you can actually pick out places in this 3 space, or like in this N space, that are special landmarky bits. Like this is a group at Stanford that did a tree generator back in like the early 2000s, and they extended that research by figuring out what the landmark trees are, so that people could like navigate the trees by saying like, I want something closer to, pine tree and farther away from palm tree, or like, you can even lerp, like, give me something that's halfway between palm tree and cactus. So yeah, you can lerp with arrays of floats, because it's just an array of floats. Although actually, I don't know that they're using an array of floats. But yeah, gameplay, I want to go through at least one other thing before this, so I'm going to go through this really fast. But gameplay, there's a couple of things that you can do with PCG for gameplay. Mostly it's been limited at this point to exploration. Just like, look at all the content. Hit regenerate. Or maybe fight a battle and you get a piece of content. Fight a battle, you get a piece of content, whatever. Spore actually did this. I think No Man's Sky is probably going to do a lot of this as well. This is great if you're not interacting with your content. But we can now interact with our content, so where else can we go? We can do procedural collectibles. This is, damn, I forgot to put sorry, shouldn't swear on the stream. I forgot to put the attribution here, but this is Reese and Stanley's lab or Ken Stanley at University of Central Florida. And they made this cool flower generator. Remember how I said flowers are easy? So they made this cool flower generator. And what they did then was they used machine learning to take this giant possibility space, figure out regions of that possibility space, picked out a flower in each region, and made those collectibles. So they actually made a gameplay mechanic out of this machine learned feature set, or like machine learned exemplar set. And now that's a gameplay